everybody. Today we're going to go through topic 5.3. It has kind of a long title, Magnetic Force on a Current Carrying Wire. So, big idea here is that magnets exert force on current carrying wires. The direction of that force, you're going to use the right-hand rule again, like we used last topic, but instead of a single charge and using the velocity as your pointer finger, you're going to use the current for your pointer finger, which should make sense still. It's still going to be the direction that charges are moving, so it's still kind of like a velocity. Middle finger is your magnetic field, and the force is your thumb. So what that kind of looks like here, if this is a wire, we picture it as positive charges moving. That's what we picture as current. So this would be the direction of I, our current, is to the right. And let's say we have a magnetic field that is pointed upward. So this is our B field. So current's to the right, magnetic field is up. Okay. What direction would the force be? So right, up. You should have your thumb pointed towards you with that right-hand rule. So the force, the magnetic force that this wire will feel, is out of the page. Cool. So charges will not move in circles like they did if it was an isolated charge, but instead the wire will just bow or kind of bend in the direction of the force. So first case, just draw a straight line. We have a magnetic field that's into the page. If we have no current, the wire is not going to change direction. It's not going to move. But let's say I have a current that is flowing up through this wire. If I point my pointer finger up, my middle finger into the page, this will have a net force to the left. So what we'll see is we'll see the wire kind of bend outward. On the flip side, if our current was down instead, point down, magnetic field is into the page, we should see that there's a net force to the right. And so this wire would bow in the other direction. Cool. That magnetic force on a current carrying wire equation is going to be how much current in amps times the length of the wire that is in the field times the magnetic field. And again, we'll have a sine theta here. This will usually be 90 degrees. So this term will go to 1 typically. So usually we'll just see ILB. So that's our equation for force on a current carrying wire in a magnetic field. That seems really specific, but it actually has a really practical purpose, and that is an electric motor. So if we have a loop of wire that's in a magnetic field and it's connected to a voltage source, and the reason we have that is so that we have a current. Okay. So we've got V, so we have I. This loop of wire will have a net torque on it, and it'll cause the motor to spin. So in this picture here, if you want like an easier picture, let's say we had a magnetic field to the right, and then I have a little square loop of wire, and then down here I've got a battery. So for this battery, let's say if I have current going up this side to the left and then down. different parts of this loop will feel different forces in different directions. So let me get a different color here. Let's do yellow. Okay. So for the current that's going up with a field going to the right, okay, we will have a force that is into the page. Okay, so force is pushing this into the page. For this branch up here, we're not going to have a force because our current and our magnetic field are parallel. But then on this side, we'll have, so that should be X's. Here we'll have force coming out of the page. Okay. So if you imagine this is free to spin, okay, we're pushing into on one side, out to on the other, this is going to spin. Okay. And this is a way that we can take some electrical energy and convert it into mechanical energy. A simple, yeah, we'll talk about practical things in class, but yeah, this is super useful and practical, and that's it for